most of this talk will be loosely based off a Blue Sky paper that I had at Amos this past year, and I'll have a link to that paper at the end of the talk. But first, I want to say thanks for having me at the seminar. Sorry I'm not able to be there in person and give the talk, but glad we kind of can do this whole virtual thing. So yeah, without further ado, the talk I'm going to give is titled Presenting Multi-Agent Challenges in Team Sports Analytics. And as Matt noted, my name is David Radke. I'm a senior research scientist with the Chicago Blackhawks in the National Hockey League. And yeah, so I'm going to start by essentially highlighting AI's pretty unique relationship with games of all different styles. So this is by no means in a fully exhaustive background, but obviously we need to include Jonathan Schaefer with checkers, since we're here virtually at Alberta, and then also chess with the development of Deep Blue. So board games have had a really interesting and been a key component in the development of AI over the last few decades. This then evolved into AlphaGo, and then agents that were able to play Go, chess, and shogi without even knowing the rules of the game beforehand. And then super recently, developing agents that learn to play the board game Full Press Democracy. Or sorry, Diplomacy, not Democracy. And so this agent is called Cicero from Meta AI. Came out around this time last year, I believe. And so this is kind of a really cool combination of reinforcement learning, planning, and language to learn how to play the board game Diplomacy at a human level. And it's not all just about board games. So we see the development of AI in various card games, such as Hanabi, which is a really cool now cooperative AI benchmark for cooperative games, and also games with imperfect information, such as poker. And clearly, like, I come from a multi-agent RL background, and so we can't mention AI without bringing up reinforcement learning and how video games have really helped reinforcement learning have benchmarks in the single agent case, and then also expand to domains like Dota 2 and StarCraft. And so these are very common to help support the development of AI in the last few decades. And these video games aren't just Atari and Dota, but a lot of these video games and games in general are often sports related. So we see with the development of GT Sophie from Sony AI, they're able to train an agent to learn how to outrace the top Gran Turismo race car drivers in the world. And obviously I need to mention the awesome progress in the last few decades in the RoboCup series, where these are both simulated and real environments where we're able to train agents to learn how to work together, and also train robots or have robots learn how to coordinate and try and like win this zero-sum soccer game. And on the right, I have a screenshot of Google Research Football, which is this really cool environment, which is essentially kind of like the FIFA video game series, where we can train agents to learn how to play soccer, a single agent or a multi-agent scenario, soccer or football, in this kind of somewhat realistic environment where we have full observation of where all the other agents are, and there's various types of actions that these agents can learn to take. And so the last few slides, I've kind of gone through some really interesting areas, different kinds of games, from board games to card games to video games. But there's also a lot of really cool progress in the general scope of AI as it relates to real world games. And so there's tons of work in computer vision trying to estimate the pose of players on the pitch or on the ice, different computer vision tracking problems, if we can actually extract coordinates and locations of players in different areas of the ice or the pitch. There's also lots of evaluations and papers. If you go through various papers at top conferences, there's a lot of general algorithms, say about team formation or learning characteristic functions of groups that work generally, but then also go and use data sets from basketball or some other sports. And obviously, I need to talk about the partnership in the last few years between DeepMind and Liverpool FC, where this is really like a major step towards a large research lab, really making the manpower investment in helping drive towards or identifying the problems in sports that are related to general AI problems. So again, this is by no means an extensive overview of the field of artificial intelligence. I'm just using it to kind of make my point that there's all these different areas of AI, such as like computer vision, NLP, deep learning. But what this talk is going to be about is essentially the role that multi-agent systems has specifically in the area of sports. And I can't really talk about multi-agent systems as it relates to sports and all the open problems that I'm going to discuss today without also including things like reinforcement learning and deep learning. So these are kind of the three main topics that I'm going to touch on in the rest of this talk. The talk is going to be split up into essentially two different areas. I'm going to first talk about multi-agent challenges in team sports analytics. This is going to take up the majority of the talk. And this is the part that's really based off of that blue sky paper that we talked about earlier. Most of the things I'm going to talk about in this part of the talk are open-ended problems that I'm identifying. It's by no means exhaustive, and it's really emphasizes the multi-agent connection to sports. There's tons of other areas of AI that have really, really cool connections to sports, but this is really about identifying some multi-agent challenges. And then I'm going to get into how some stuff that I've done at the Blackhawks, where we can actually learn value functions from data that happen in real games in the NHL. So first, multi-agent challenges in team sports analytics. In the early 80s, Ellis published this paper that essentially takes real-world sports games and divides them up into classes. And so two of the classes I'm going to talk about are here. The first is striking games. So striking games are those where players strike objects into open spaces and place fielders, and the other team places fielders strategically to prevent runs from being scored. Some examples of striking games are things like baseball and cricket. And so the last few decades have really seen this wild analytics revolution in baseball specifically, the striking game of baseball. And so this is known through the overarching concept of sabermetrics, but it was popularized through the book and later the movie called Moneyball. And the idea here is to essentially use empirical statistics as a basis for roster management. And these are things like using on-base percentage, slugging percentage, and batting average initially to try and figure out how you can score more runs than your opponent. And these days, obviously it didn't stop there. These days, the way that baseball teams are coached and managed and operated relies heavily on all of these different types of statistical models. The next type of game I'm going to talk about are those called invasion games. And so invasion games are those where teams intermingle and attempt to outscore the opponent by invading the opponent's territory. And some examples of invasion games are, say, ice hockey, football or soccer, and basketball. And so invasion games haven't really seen this thorough revolution of analytics that games like baseball have seen. And that's because there's a lot more interaction, a lot more coordination required to be successful, and there's a lot of teamwork. In baseball, if you want to score more runs, the way that baseball teams generate offense is you essentially have one player go up and try and generate offense one at a time. And sure, there's some coordination between who's on base and you know, what role in the batting order you are, but that can all essentially be boiled into the state space. And so it's kind of like a problem where you try and have one player go and generate as much offense as possible. And if you stack up those players one by one, you're likely to generate more offense. But in invasion games, generating offense is a lot more complex. There's a lot more strategic freedom, and there's a lot more actions that players and groups of players can take. And so in invasion games, it's not just about who is good, but it's who's good together and in what scenarios. So the main idea of this part of the talk, and kind of this whole idea that I'm gonna talk about, is that I believe multi-agent systems is to invasion games what statistics was to striking games. And so progress at the intersection of multi-agent systems and invasion games is really going to be necessary to help bring invasion games through this analytical revolution that striking games have experienced over the last few decades. Some high-level points on why I believe that like studying the intersection of these two areas is useful. Invasion games are operated within enclosed environments, and they're governed by rules, kind of essentially like the video games that we train agents in. There's real examples of coordination and cooperation, and these are both good and bad. You know, sometimes we see a line in hockey that really gels, but a lot of other times we see a line that just doesn't. The teams that operate in invasion games often have structure, and there's hierarchy to the teams. In hockey, we have forwards and defensemen. We have different lines of forwards, different lines of defensemen. So the interplay between these hierarchies and how to deploy these hierarchies is also an interesting question in its own. There's multiple timescales in these games, such as planning for coaching in the next match or in the current match, versus planning over long time horizons, the management problem of how do you actually construct a team that's able to generalize to end opponents and win a league. Or maybe this is across multiple seasons. And what's really cool is that in professional sports, this is all augmented by marketplaces. Players sign contracts for a fixed amount of money, and teams often have a fixed amount of capital that they're allowed to allocate to players that they want to sign. So there's a lot of financial transactions that kind of are in the background of a lot of these problems. And another really cool thing is that we can get a lot of data on these problems. So I'm just going to highlight two of the in-game data sources that we get, just to kind of give you an idea as to how we can use this data and approach problems using these types of data sources. So the first is event data. And this is not unique to hockey. There also exists event data in basketball and soccer and a lot of these games where there are actual on puck or on ball actions. So these are things like shots, passes, carries, possession gains, stuff like that. And so the data we get on these events is essentially the XY coordinates on the playing surface, the players involved, the time of the game, score differential, stuff like that. Just trying to capture the state of the game when this event occurred. And so I have this figure on the right, which essentially shows that these events, when strung together, kind of create a Markov type chain. And if you were at the talk a few weeks ago, Oliver Schulte discussed this type of data and some of the work that he did. And so there's about 3,500 events per NHL game that's citing the 22-23 season. And it's kind of this Markov chain looking series of events. However, these events don't just come from one player or one team. So 2 rows might come from team A, 2 different players on team A, and the next 10 rows might come from the other team. But the events kind of happen sequentially through time. The other source of data that we get at the NHL level, and in soccer, this is kind of more widespread because it's an easier computer vision problem in soccer, is tracking data. And so tracking data gives us the X, Y, and Z coordinates of all of the players and the puck or ball on the playing surface multiple times per second. And so if we do a join with tracking data and event data, we essentially get kind of a better look at what the state space was when there was a pass or a shot. We can say, instead of just saying there was a pass from A to B, we can say there was a pass from A to B and all the other players on the ice were in these locations, traveling at this speed in this direction. And so it really kind of gives a better view of the state space. Not a complete view, because in the NHL we don't have stick tracking, but you get kind of an interesting look at the types of plays that happen in different situations. And so the next slide, I don't know if I'm going to freeze on the next slide because it's a GIF, but it's essentially some work I did analyzing passing lanes with NHL tracking data in past work. But it really just gives you an idea of what the tracking data actually looks like. And so there's going to be a bunch of numbers, but those are just passing lane values. But essentially, you'll just see players moving around. And so here, this is a face-off. There's two teams, and there's this pass off the wall. And you can see that there's all these vectors that show how players are moving. And so this ends up being a goal. But I'll just let this play through a few times because it's pretty cool. Cool. So we get tracking data for every single game in the NHL, and we get event data. And again, we can do a join on them so that for every single event, we have a view of whatever the state space looks like. And I'm just going to address this question quickly because it's related to that GIF. So the numbers represent, this was just a GIF from previous work that I did in analyzing passing lanes. And so not related to this talk, but the numbers above the players represent how available each passing option is to the defenseman who made the pass. So I'll just go back. You can see it's 1, and this defenseman has various passing options. But yeah, so thanks for the question. But so yeah, moving on with this, I'm going to identify basically 2 different axes of problems in the sports world and how there's relevant multi-agent topics to help us try and approach them. The first is coaching. And so these are short-term in-match or pre-match problems where we're really trying to make adjustments for the direct opponent. These are zero-sum situations. The next is management. These are longer-term questions throughout an entire season or multiple seasons. And one point I really want to emphasize is that these axes don't really operate in isolation. Whatever coaches do in the match ultimately impacts the number of points that the team gets throughout an entire season and the kind of the situation that management finds themselves in when they try and make decisions. Are you buyers or sellers at the trade deadline, or is your draft position in the top 3 picks or lower down in the order? And obviously, whatever decisions management makes in bringing players in, trying to construct a team, ultimately impacts the ability for coaches to plan for the opponents to try and devise winning strategies. So first, I'm going to talk about problems in coaching. And so again, these are before or within matches. These are zero-sum settings where you have one team and you have another team and you're trying to beat that single team. And so some common problems that coaches often have to deal with are understanding which players play well together. And in doing this, coaches often need to try and come up with a measure of how much do individual players or groups of players contribute. And ultimately, coaches need to devise and then update strategies to try and beat their opponents in this zero-sum game. And so I'm going to pause here just for a second. With these 3 problems, usually when I give this talk, it's to like a purely multi-agent background or audience, but I'm just going to pause and want you guys to think, given whatever your background is, of how you might approach some of these problems. So I'm going to, on the next series of slides, I'm going to highlight some multi-agent, high-level multi-agent topics that have kind of overlaps with each of these problems. The first, to try and understand which players may play well together. This is essentially trying to understand the team formation problem, or the coalition structure generation problem. Which players can form these subgroups within a population and end up having the highest expected value. To do things like this, it might be good to understand agent types. There's often, even though we have forwards and defensemen, there are things like offensive defensemen and defensive defensemen. And so understanding the distribution of agent types can help us actually with this team formation problem. Things like offline policy evaluation. It's also really valuable in trying to understand the value decomposition and credit assignment problem of how much do individual players or groups contribute. A group of 5 players may go out and score a goal. And sure, we can assign a goal and an assist or 2 assists, but actually understanding other things that happen on the ice and plays that lead up to maybe that scoring play may be significantly valuable in understanding how much individual players or groups contribute. Finally, in this whole zero-sum dynamic of devising and updating strategies to beat opponents, things like opponent modeling, actually trying to understand and predict things that your opponent might do in different situations, is very valuable. There might be multi-objective optimization. So in a hockey team, we have 4 lines of forwards. Not every line can ultimately go out and have the line-based goal of generating offense. Like sometimes you need a line to match up against the other team's offensive line. So multi-objective optimization by having some lines with the objective to generate offense and other lines that might have the objective to reduce offense for the other team. Things like game theory and mechanism design, these are obviously like really high level problems, but I'm going to dive into game theory a bit more, but there's a lot of work in empirical game theory and understanding, given this high level strategy, what's my best response to a different situation. So I'm just going to go ahead and dive into some of these just to highlight some relevant multi-agent work and relevant work in the domain of sports. And so the first is agent types. Now, agent types is not new to multi-agent systems, and it's not really new to sports either. But these two kind of areas are evolving on their own, and there's not much tie between them. And so agent types, there's been a ton of really good work out of Peter Stone's lab at UT Austin, trying to understand agent types in ad hoc teamwork. These are settings where agents basically need to try and do zero-shot coordination. They're not trained together, and one agent might be beneficial for one agent to try and learn the type of their new teammates. Because then, if there's a missing type, they can try and fill that gap. So this is estimating teammates' roles and abilities might help the agent learn how to coordinate with their teammates. And what's also interesting is that these roles may also be dynamic. So it's not like agents have one specific role, but this picture on the right here comes from a 2019 paper where maybe your teammates switch roles in the middle of an episode. So to actually try and understand that and react to that is pretty interesting. I mentioned that agent types is not new in sports. And so I just going to highlight some work going on in sports, and this is estimating positions from data. This is a big topic in research in soccer, where different formations essentially change how players in different situations or in different positions play. So one player might be more offensive in a certain team formation or more defensive in a different team formation. So to try and understand exactly the position of a player is a really interesting open problem. On the right, this is some of that passing work that I did with the NHL tracking data, and we found some really interesting trends to differentiate forwards and defensemen in their passing patterns, and then also within forwards and within defensemen, there's different types of defensemen with how they pass the puck, and different types of forwards with how they pass the puck or how they position themselves. On the bottom here, we found a really interesting trend where the x-axis here is assists. So players on the right are those that get a lot of assists in a season. And on the y-axis, we show passing lane. So this is kind of that GIF I showed earlier, where we were trying to measure kind of, do players make passes through really small areas or very large areas? And what we was, there was this trend that kept coming up where players that do get a lot of assists and are traditionally measured as good passers because they are able to get a lot of assists, don't typically make passes with very large passing lanes. They always try and thread the needle, if you will, or their averages always tend to be lower. I mentioned earlier that I'm going to dive into game theory here, and this one's really interesting from kind of a relating multi-agent game theoretical perspectives to sports. And so the first, obviously, game theory is like it's like a big area, and I'm not going to be able to go through all of it, but there's some really interesting work that I want to highlight on kind of the multi-agent side, and that is transitive and intransitive strategy spaces in sports, or not in sports, in multi-agent systems, and just in games in general. And so on the left, I have this work out of DeepMind a few years ago. There's this awesome paper where they essentially tried to map the strategy dynamics in games onto this spinning top geometry. And so they end up taking different types of learning, such as like self-play, fictitious play, and they actually like map them onto this geometry, where the lateral axis is essentially transitive games or transitive strategies, and then the vertical axes are intransitive strategies. And on the right, this is recent work out of Mila, which really tries to learn from data kind of the properties of ELO games, or games that are transitive, or compared to disc games. And so these are games where strategies, there are cyclical strategy spaces. And so these are related in a way to Invasion game sports, because there's a lot of cyclical strategies, and it would be really interesting to identify these from data. But there is a lot of existing empirical game theory in sports. And so on the bottom left, this is from a really nice paper out of DeepMind on what can AI do for football. And they essentially go in and peel away this little zero-sum game in football or soccer, which is penalty kicks. And so how should a left-footed or right-footed player kick the ball in a penalty kick? And so they do empirical game theory and essentially learn these payoff matrices for different styles of players, or like types of players in terms of left or right-footed. On the top right, this is work in kind of maybe a best response, or like understanding weak points in different teams' formations in soccer. So you can see there's two different formations, and learning kind of trends of where weak points are in those formations. And then on the bottom right, this is from baseball, so a striking game, but it is kind of an interesting use of empirical game theory where they learn value functions conditioned on the batter. And so given this batter, where is your area of highest value in pitching, given kind of the strike count and where you are in the game? So multi-agent systems and kind of algorithms in multi-agent systems are not a silver bullet to the sports world. There's going to be a lot of work that's going to have to happen at the intersection. And so some challenges for the multi-agent community in trying to solve a lot of these problems are understanding that players are dynamic. They don't just have frozen weights and we put them out in the game and say, okay, go and we'll simulate the game. Players essentially adapt on the fly. Maybe to a change in the game state space, or a change in their opponents. There's players and groups with different tasks and goals. I talked earlier about how different lines might have different goals. And so depending on the situations that lines are put in, players' goals, individual goals and incentives might actually change. I talked about how tasks and goals may be dynamic. So maybe a line that is supposed to shut down the opponent's offensive production, towards the end of the game, maybe they might want to become more offensive if their team is losing by 1 or 2 goals. So to identify the shift in goals, shift in the environment might be an interesting problem. And there's also variable incentives among players. Like I know in the multi-agent community, whenever we use sports or we use these simulated environments as test beds, we treat two-team zero-sum games as kind of a cooperative, competitive setting. But in the real world, in real sports, every time, like maybe all the players want their team to win, but they also might want to score the goal that wins their team the game. Because if players are the ones to score more goals, they likely end up getting a larger contract. So it is kind of like, even though it is a cooperative competitive setting, there is a bit of mixed motive incentives mixed in with the individual players on the team. And there's also individual and group policies and agency. This is something really interesting where agents do take their own actions, but they often work as a group. Lines often have plays that they run. And so there is some notion of group policy and group agency. That's the coaching axis. Now I'm going to go into the management axis. And again, these are really longer term problems that might cover an entire season or multiple seasons. And so I'm going to go through kind of the same setup here. And first, I'm going to analyze some problems that general managers often have to deal with. And these are things like analyzing a roster to identify areas for improvement. And once you've gone ahead and analyzed your roster, you need to actually construct a team through drafting, signing, and trading. These are different ways that you can acquire players. And what's cool in professional sports is that this all needs to be done within economic constraints. So in some leagues like the NHL, we have a hard salary cap, and every single day you need to stay below that hard salary cap unless it's the off season. There's different rules. There's tons of different constraints on that problem. But other leagues might have a soft cap or not have a cap at all. And then your economic constraint is how much is your owner or your management willing to spend. So I'm going to take just a few seconds here again and pause here and let everybody think about how they might pretend you're a general manager of a team, say the Edmonton Oilers. How would you go ahead and approach some of these problems? Okay, so some of the things I came up with as it relates to multi-agent systems are understanding role diversity and distributions among a team. So if you have a team of all small elite goal scorers, you might not actually win the Stanley Cup because maybe that isn't the most that's maybe not the most optimal team structure. To analyze your roster, things like offline RL might be useful, or policy evaluation, multi-agent policy evaluation, to try and understand how good individual or group policies are when they're put together. Things like behavior cloning or imitation learning might not just be good for analyzing the roster, but also when we're trying to construct a team. If you're able to perform imitation learning on a player from another team or maybe a different league, perhaps you could figure out how that player might work well with some existing players that you have. Maybe some notions from ad hoc teamwork come in because these players have never played together. Maybe you can understand and predict how well they might work together. So this brings in some notion of policy prediction, which is interesting. Given two players that we draft at 18 in the NHL, we draft players when they're 18, but they don't reach the NHL until years down the road. So are we actually able to predict how two players might develop over the next few years? Two players might look the exact same at 18, but end up on wildly different trajectories based on what leagues they're playing in, who they're playing with. When constructing a team, game theory through drafting is an interesting topic where there's obviously a lot of game theory involved in trades, but also drafting strategies. And so within economic constraints, this is a really interesting way that this all kind of ties into the computational social choice community for things like resource allocation and fair division. Uh, Teams have fixed amount of capital, and you need to be able to allocate that capital across a team, perhaps in a way that there's not, obviously there's gonna, you're not gonna be able to be envy free based on like everyone would obviously want more money, but some sort of fair division where if you have Connor McDavid on your team, obviously he's going to get paid more than someone who is not Connor McDavid in a sense, or like maybe not close to being the player Connor McDavid is. And then when signing players, there's obviously bargaining and negotiations that come into play. So the first that I'm going to dive into here is the idea of role diversity and distributions. In multi-agent systems, there's been several different works that look at how diverse teams are actually very strong and sometimes stronger than teams with, say, expert agents. And so I cite a paper here from 2004 where a group of suboptimal Go playing agents were able to actually outperform the top playing Go agent at the time. On the left, some work that I did in my PhD, which was to understand how teams of different sizes ended up having agents with different distributions of roles and how the distribution of roles really impacted the efficiency of different teams. And on the right, some work that Patrick McAlpine did at UT Austin in his PhD was really to look at different roles on a soccer team in the RoboCup environment. And obviously, this is a big topic in sports where on the left, I believe Oliver Schulte shared almost this image exactly a few weeks ago where one of his students essentially learned player embeddings from offline event data. And so understanding different embeddings for centers, wings, defensemen is a really interesting problem. And on the right, understanding in a sport like soccer, how different players in different roles or different positions can learn to work together and how well they work together. The next one of these topics I'm going to go into is game theory again, but this is now on like the broader management side. And so I mentioned draft strategies before. The way that players acquire or teams acquire players in the draft is essentially the teams are lined up in a cyclical order, and there are rounds to the draft, and you're able to pick from any number of draft eligible players. And so there's a lot of work in picking sequences in things like computational social choice and the game theory behind how should you pick things out of a bin. And obviously agents don't just pick the thing with the next highest expected utility. Agents have different preferences over goods, much like teams have different preferences over, do we want offense or defense, or maybe a goalie? Like if all the public rankings were perfectly accurate, then the draft every year would follow the exact pattern that these public rankings that people make. And so in sports, there's been a lot of work in trying to actually measure the probability of the next player being chosen. And so once you have the probability of a certain player being around at a certain pick, teams can sometimes ask themselves the question, do we select the best player on the board right now, or do we select the best player conditioned on the probability that they'll still be around at our next pick? There's the notion of draft efficiency too. Maybe some teams will have 5 draft picks within the first round on 1 year, and one of them turns into an all-star player. Or some team only has 2 picks in the first round, and both of them turn into all-star players. These are things that retroactively people have looked back to try and measure. And again, some challenges for the multi-agent community when trying to address some of these problems are things like predicting policy development. I mentioned this thing of you get players at 18 and trying to predict how they'll develop. There could be many different policy types for the same goal. You can have a player who plays like Connor McDavid and a player that plays like Leon Draisaitl, and maybe they both just want to generate offense and they're better together, but they have very different playing styles. you need to be able to construct a team that's able to generalize to 31 other opponents in the NHL scenario, not just conditioning on the opponent you play on Friday night. These teams need to be robust to injuries. Sometimes, like we had Taylor Hall last week, got injured for the rest of the season. So we need to be able to build a team that if a player gets injured, we're still able to be successful over the course of the season. And these last two that I'm going to just emphasize because they're really interesting fair division problems are the fact that contracts have different term lengths. So players might sign for 1 year, or they can sign for up to 8 years. And so this isn't just a fair division problem at the point of signing or at one point in time. These are temporally distributed problems. And so management often has to think about, what do I want my roster to look like 5, 6, 7 years down the road? Even though there's a fixed salary cap, there might be some talk of the salary cap going up, but they need to try and sign players to contracts over time based on their past and projected performance. And so these aren't just fair division problems right now, but they end up being temporally distributed. So next, I'm gonna quickly go over at a high level some of the work that I've done with the Blackhawks during my time there. And this is about learning value functions. And so this is a generalized value function, say for the entire league, based on the incoming event data. And so the goal here is to try and learn the value of a specific state of the game. So there was an event that happened on the puck at this coordinate, at this time of the game, and all these different game states situations. And we want to learn the actual value of that event, of having possession or doing something on the puck at that point in time. And so the challenge here is that the event data we get isn't just from one team or from one player on that team. There's a bunch of different players that belong to two different teams, and these teams are adversarial, and these players play different positions. And so every time there's an event, it could come from any player from either of the teams. And so we have this defined reward structure in the games. We have a goal, we have a shot on goal with some probability of going in. But there's some challenges in here. So I'm going to talk about basically how we kind of go about overcoming these challenges in the incoming data stream. And so just to formalize some of these challenges, these games are not simultaneous move. It's not like in the real world, essentially, team A takes an action, players on team A take an action, and players on team B also take an action. But in the event data, what we see is not a simultaneous move game. We essentially have one team doing something on the puck at time t, and then at time t plus k, the next event ends up happening. And these events are also not Stackelberg. So it's not like team A moves, then team B, then back to team A. Team A could essentially perform 3 different events on the puck, and then team B could perform 10 different events on the puck. And as I mentioned earlier, the actual rewards that we get from the game are pretty sparse. Goals, there's maybe an average of 6 or 7 goals per game in the NHL. And there's a lot more shots, but these shots are still pretty sparse in the grand scheme of things. There's 3,500 events, and there's maybe less than 100 shots per game. But given those challenges, there's also some advantages in the structure of how games are played. We know that within a match, it's going to be a zero-sum game at the level of the 2 different teams. So we know there's not going to be a third agent that comes in and starts generating data. There's exactly 2 teams, and that it is an advantage that we have this defined reward structure. We know what's valuable, and we know to win a game, you need to get a goal. Or a shot on net with some probability of going in. And so I'm going to borrow a strategy from similar work in adversarial value decomposition. And this is to essentially include this beta term in the Q value update, which indicates whether your team was the one to collect the reward at the end of the trajectory or not. And so I'm just going to show some results, and I'm being purposefully very high level and vague here. But essentially, some of the results, or I'm going to show you a model that was trained over the 22-23 NHL regular season. There were 4.2 million events in this, just over 1,300 games, and there were 1,000 players in this data set that played for over 32 teams, or sorry, exactly 32 teams. And the first thing we want to do when we want the value function, it's essentially we need to combine not only Q values, but the probability of events in different situations. And so what we can do is we can perform some notion of behavior cloning and learn a policy from data in a supervised way. We just pass in the state of the game at different areas of the ice and different scenarios of the game. And we want to say, given this state, what is the probability of any different action? And so each of these ranks represents a possible action or event that the agent or the players do in different settings of the game. These are things like carries, dump-ins, passes, shots. And so darker red here essentially represents a higher probability of this action happening at this state on the ice. And so this is a softmax output of a policy network. And so if we essentially just stack all of these on top of each other, it would just be ones across the board. So all of these ranks sum to one at the same XY location. Next is to actually learn the Q values of these actions. So given the state at each different location on the ice, what is the expected value of taking action pass or shot or reception? And so here we can actually learn the Q values given the value-based update I showed a few slides back, and we can essentially learn the value of a dump-in at different areas of the neutral zone, and the value of a reception at different areas of the ice, a value of a shot. And we see on the bottom right, the value of the shot is essentially has higher value, or it's more red closer to the net, which intuitively makes sense. And we see similar things for the reception and the puck protection, but there's maybe different shapes of where this value is. And so now that we have a policy model and we have Q values all over the ice, we can essentially just combine all of these and come up with an overall value function for the rink or for the game of hockey. And so here, darker red indicates more value. And what's really cool is that once we have the Q values for different states on the ice, we can essentially do something like say, show me the action that has the highest expected value at different states of the ice. And again, this is only from event data. So this isn't by any means saying a player that chooses to do something else in these spaces is doing something wrong, because the situation might be different. But this is just all an expectation over event data. And so what's really interesting here is that this yellow represents a shot. And so shooting has the highest value all over the offensive zone, except for these settings when you get deep in the corners. And deep in the corners, we see that actually passing the puck has higher expected value, because you're likely to pass from here to an area that might have higher expected value from the preceding shot. Yeah, except if you're dry sidle, the entire thing might be passing. And so finally, I just kind of want to emphasize that there's no shortage of multi-agent problems in team sports analytics, and that advancements in both team sports analytics and multi-agent systems, and at the intersection of these two fields, will really help drive both forward. We have real data for cooperation, development, policy development, how agents develop throughout their careers, and this is all augmented by financial transactions. There's multiple levels of planning required for success at sports. You need to be successful at the coaching level to actually win games, but you also need to be successful in generalizing to all of your opponents, building a team that lasts for multiple seasons. And finally, it's not just that we would end up giving our agents rewards like we do in standard video games, but there's also some pretty cool rewards if you're successful for the people involved. And finally, I'm just going to highlight some current areas of interest. I talked about value functions. This obviously is a lot more complicated than the slides I showed here, we have tracking data, and so you can maybe learn value functions of the tracking data. And there's a lot more different things you can do once you have a value function. So just general problems in that domain. There's things like offline policy evaluation. And so this is an interesting case because we have an offline data set. How can you thoroughly evaluate the policy that a player has from that data, both at the individual level and the group level? How can you learn a characteristic function for a group? This ties in things like team formation, maybe learn Shapley values of how much players contribute to different groups. Learning player and agent types. This is, I kind of went through how this is a big problem, but like a big open problem, but understanding how different types of players work well together is one of my current research interests. And then also empirical game theory. I talked about how this was done in soccer and baseball before, but actually pulling notions of empirical game theory into hockey and trying to figure out and help coaches make decisions is a very interesting topic that I'm interested in. So I put a QR code to the Blue Sky paper and included my email if you're interested. But it's just a 4-page open-ended paper if anyone feels like reading it. So yeah, thanks for your attention. And I'm open to any questions that you guys have. Matt, I don't know if you're talking, but you might be muted. But there are lots of questions in the chat.
Oh, so no, you couldn't hear us.
No, what were you saying?
We were all clapping. You're amazing. So maybe you could pick some of the questions in the chat and read off what you're responding to, because we can't all see them.
Yeah. Okay. So yeah, I'll just pick some of the ones here. Are there any metrics that are predicted of the team momentum phenomena? Yeah, great question. So I know the office at the NHL has tried to work on this, and there's also some people who do public work given like shot data that do this. Obviously, momentum is like not a well-defined concept, but there is work on like shot frequency, and so teams that are out shooting the other team a lot end up gaining more shot momentum, as you would think of it. And so yeah, there's some work there. So another question, can you point to successes in sports analytics with respect to coaching, team? How did you deal with counterfactuals, confounders? Yeah, great question. So I think successes in sports analytics as kind of a fully fleshed out concept can really be looked at in baseball. More like baseball has really, the game of baseball itself has completely changed with respect to how it's managed and coached. Every baseball team has a staff of dozens, sometimes up to 45 or 50 engineers, researchers, analysts that are trying to always get a little bit better and help management just kind of give management more information for how they make decisions. And this kind of also went on the defensive side of baseball, where you ended up seeing things like the shift, where it kind of changed how teams were playing defense in baseball. In terms of soccer, so I know Liverpool, and I showed it with the partnership with DeepMind, but I know Liverpool has grown a pretty significant analytics group. I think in like at least a few years ago, they had a pretty significant analytics group. And they ended up winning the league in 2019, I believe, the Premier League, for the first time in decades. And so they really kind of like put a lot of emphasis on that. They ended up climbing the table and ultimately winning. in hockey, it's still it's very new. It's fairly immature compared to other sports, mostly because of how complex the game is. And so you end up getting pushback with respect to, not from personal experience, but I know that like the general hockey community has gotten a decent amount of pushback from traditional hockey management, I guess, or hockey thinkers online on Twitter. At the Blackhawks, we're fairly fortunate in our situation where our management staff has kind of intentionally invested in building out the analytics department. The whole management is just about 2 years old at the Blackhawks, like in our positions. And so our group has really grown in the last year and a half, and we have expectation to continue to grow and really kind of take what's been done in baseball into hockey. And this is part of the reason why I have a job as a senior research scientist, because they are interested in building out kind of a multi-agent focused lab or like research group within the front office to try and like understand these problems where methods from other sports maybe don't translate as well. With your experience in the NHL, do you see some kinds of analytics more easily accepted by the organizations than others? Yeah, great question. I would say it depends on the problem that whatever the metric or analytics is trying to solve. So, for instance, there's this notion of expected goals where it's the probability of a shot going in. That's kind of an easy to understand concept. Like there's always some probability of a shot going in. Some shots are more dangerous than others. That has been fairly accepted. There's obviously some edge cases where people might push back on some of those. But yeah, definitely there's also notions. We haven't quite gotten to the point of like suggesting pairs of players to play together or lines, but I imagine that will be like probably harder to implement than like the concept of an expected goal. So yeah, probably. In my experience, no. Though we end up developing models and vetting them and getting output, and then we have an internal platform where we kind of share them, and we have open discussions with our general manager and assistant general managers, and they're very curious and very open to things that we have to say. For learning value functions, did you use other state observation features besides location? Yeah, great question. So the things I just showed you were from a tie game in the second period, but essentially the model that learns this value function is essentially the state space takes in a whole different number of things, like the manpower situation, how many players you have on the ice, the other team, what score of the game, what's the score differential in the game, what time of the game is it. There's tons of different features that actually feed into the state space. I'm surprised you were focused on key functions and not state value functions. It seems most of the value you'd want is in the state value functions, and this would allow you to just simply treat the event sequences as a Markov chain, maybe even fit the data with powerful transformer architectures. Thoughts? Yeah, really, really great point. I will say that is something that we are curious about and looking towards. The idea of just focusing on the Q function and essentially just trying to roll up the value function was to feed it into some existing architecture that we had in terms of like if you have the value of different areas of the ice and kind of rolling it all together, how we could kind of feed that into an existing model. But yeah, we do have, I just kind of gave like a high level overview of one of the problems that we tried to solve with that. So But yeah, thank you everybody for the questions.
Thank you so much, David. Well, thank you one more time.
Thanks. And if you guys have any other questions or interest, feel free to reach out to me. Thanks again. I'll just stop sharing my screen. But thanks again for inviting me. And yeah, this was great.